To understand how fires can spread between shelters, it is first important to understand how a shelter will burn. Fire engineering for urban contexts traditionally is based around the idea of the compartment fire. The idea of the compartment fire can apply to individual rooms within a building or a small structure such as the shelters that Kindling tested. Let's understand it in the context of our cement block shelter with a metal sheet roof. When the compartment boundaries, the walls and ceiling of a room or shelter such as this, are non-combustible and robust, the hot gases that the fire produces as it grows will collect in the top of the room, what we call the compartment, at the roof level. As the gas collects, it radiates heat towards the rest of the fuel on the ground, helping the fire to grow faster and faster. During this stage, there is still plenty of air containing normal oxygen levels within the compartment, so all the gaseous fuel can burn inside. However, there comes a critical transition phase when the heat contained within the compartment is enough to ignite all the fuel within it. To observe it is to see something on fire inside a room becoming a room that is completely on fire. We call this transition flashover. After this, the fire generates so much fuel gas that clean air, and with it the vital oxygen, cannot get into the compartment quickly enough to burn all the fuel gases inside. The temperatures inside reach 1000 degrees Celsius. The hot fuel gases escape out of the open windows and doors, mixing with the fresh air there and then burning outside. We call this the external venting flame. External venting flame is hazardous. The temperatures in the flame at minimum exceed 500 degrees Celsius, but can reach to over 800 degrees Celsius. Direct contact of the flames on a neighbouring shelter, we call this flame impingement, will almost certainly be enough to ignite it if there are combustible materials present. This is because the ignition temperature of most combustible materials is far below the temperature of the flames. For example, most types of wood will ignite when they reach temperatures in the region of 250 to 350 degrees Celsius, far below the temperature of the flames. But even when there is no direct flame impingement, anything in the close vicinity of the flame still receives a high level of thermal exposure due to thermal radiation. And the closer a neighbouring shelter is to the flame, the more radiation it receives, potentially to the point of ignition, with no direct flame contact. Our cement block shelter is a very good example of this. You can see that at the door and window, flames are projected outwards, and we recorded those high temperatures and heat fluxes on the nearby instrumentation. However, away from the window and door, like at the end walls of the shelter, there are no flames to present a hazard to a neighbouring shelter. This is a pattern we saw with any type of shelter which has a broadly non-combustible facade material. First, we can see what happened when we have mud walls rather than cement block. Here we used a wattle and daub style construction containing a clay mud mixture plastered onto a wattle wood frame. So this does contain combustible material, but is largely encased within the non-combustible mud mixture. It showed very similar fire behaviour to the cement block shelter, with comparable temperatures inside and high heat fluxes registered from the door and window. We also tested a metal sheet shelter, which showed some flame leakage in the gaps caused by corrugation of the metal. After the shelter collapsed, there was still a hazard from fuel burning underneath the pile of metal sheets. These are extra hazards that we don't necessarily see from the cement block or mud shelters. However, the main hazard for all three is still broadly the same. That is, flame impingement and radiation from the large external flames at the window and door. But what happens when we start to use combustible materials in the shelter facades? We performed 3 tests that still have metal sheet roofs, but this time with combustible wall materials: timber, split bamboo, and a woven bamboo mat. They all showed similar fire behaviour over the test. As the fire grows, the internal walls are being heated towards their ignition temperature. by the hot gases collecting in the top portion of the compartment. When sufficiently heated, they ignite, helping the fire to grow rapidly. At this point, the fire also transitions to the external facade of the wall. Now the fire spread hazard is not only the flames projected from the window and door, but also the high heat fluxes and the potential for flame impingement around the whole shelter as the wall burns. There is some variation between the three materials, which largely depends on their thickness. For example, the timber is the thickest of the materials. It took a little longer for the fire to establish on the wall, but when it did, there was a prolonged 5-minute period that it was exposing the surroundings to very high heat fluxes in all directions. The bamboo materials, being much thinner, ignited more quickly and also burned away much quicker, resulting in comparably high heat fluxes as the timber shelter, but with peak exposure conditions occurring for less than 1 minute. After the walls have burned away, it is no longer possible to define the fire as a compartment fire, since there is no limitation on oxygen getting to the fire. There are no external flames specifically from the door or window, as these are gone. However, this does not mean the potential for fire spread has ended. If there is still fuel in the shelter, it will burn as an open fire, with flames spilling around the edge of the roof. Additionally, a combustible wall doesn't just increase the fire hazard due to external flaming on the wall, but it does also increase a shelter's vulnerability to ignition. Simply, a timber or bamboo wall is a large area of ignitable material, where an equivalent cement block or mud wall is not. We also did some tests to examine the effect of combustible roofs, the most common of which is thatch. Like combustible walls, these present a different hazard. In the tests, we saw that when the roof caught fire, gaps would form as the material burned away. This changes the compartment fire conditions because the hot gases inside can ventilate upwards to escape, rather than collecting at the ceiling and then being projected from the door and window. In these combustible roof tests, there were almost no projected flames from the openings. Instead, high heat fluxes all around the shelter were caused by the burning roof. This is a considerable new hazard whether the walls are combustible or not.
1, 2, 3, go! We're expecting a lot of heat like we had before.
In contrast, we also did one experiment with a split bamboo roof and bamboo mat walls.
We've got good ignition.
After an initial period of intense burning as the walls burned away, the fire didn't establish consistently on the roof, in comparison to an equivalent thatch roof test. What does this tell us? Well, the experiments show that different combinations of wall and roof material will generate different fire hazards. Different materials react to fire differently and burn differently, beyond simply whether they are combustible or not. On this subject, you can find out more about why thatch is particularly hazardous on our next video.
Final check. We have ignition.
One fire spread hazard that we know exists, but were unable to properly study in these experiments, is the possibility for fire to spread due to firebrands. These are small pieces of material that break away as the shelter burns and are lofted and distributed by the buoyant hot smoke plume. Not all materials produce these, though we did see many of them being produced in any of our tests with thatch and bamboo mat. In the case of thatch, these were small pieces of thatch reed, but in the bamboo mat test we even saw large pieces of charred mat being lifted away from the burning shelter. If the firebrands are burning or are still hot after burning, there is a chance that they may be able to ignite any combustible materials in the surroundings. But the whole process is difficult to capture in large outdoor experiments. The overall spread of fire by brands depends on the number of brands produced, the ability of the smoke plume or wind to loft and distribute the brands, and whether the brands release enough heat to ignite the exposed material. In many cases, ignition by firebrands actually requires the accumulation of lots of them in one location. We had nothing in place during the experiments that allowed us to quantify any of this, but did at least discover that the thatch and bamboo mat produced large numbers of brands, certainly compared to the rest of the tested materials. The general conclusion to all these tests is that context matters. Any single material will present different hazards in combination with other materials, and there are trade-offs at every turn. A metal sheet roof will always cause the projection of flames laterally towards neighbouring shelters, but to a lesser degree if the walls have burned away. But then if the walls do burn, even for a short period, they generate very high heat fluxes around the shelter, rather than just near the window and door. A combustible roof will vent hot gases and flames upwards, rather than laterally outwards towards other shelters, reducing the chance of flame impingement. But again, the combustible roof is itself a new source of burning and can generate high levels of radiation around the shelter. Approaches to reducing fire spread must then be diverse. There is no one-size-fits-all strategy that can account for all materials in all configurations. But these experiments set a precedent by which different combinations of materials can be understood, and strategies for mitigating fire spread can be targeted to suit the materials and context of different settlements.